Hi, my name is Tyler Browen, and on behalf of MECH 400's Group 1, I'm going to be presenting our concept for a hybrid electric multi-person vehicle. Our client for this project was the UVic Facilities Management Organization. They wanted us to build a 10 to 12 person bicycle with optional electrical driving components. The client also wanted us to include competition aspects between each rider in the vehicle, as its main purpose is to be used for team building exercises. The client needs and user requirements are as follows. First, the design should incorporate off-the-shelf components. This will reduce manufacturing costs and make maintenance and building of the design much easier. Second, it should be electrically assisted to make for a more exciting design and more opportunity for the competition aspects. The design should also be scalable, so that upon receiving the final draft of our design, the client can choose whatever size he'd like to build. Lastly, our design needs to be aesthetically pleasing so that it stands out as an innovative solution. Here is a more detailed look at all of the client needs that encompass the scope of this project. As previously mentioned, the design we decided to go with is a hybrid electric concept. The flowchart on your screen gives a high-level overview of exactly how it works. Each rider pedals mechanical input into a gearbox and generator, where DC power is produced. After this, a series of regulators and diodes control the voltage and current going into a central bus bar. A motor controller then collects power from a battery and the bus bar and distributes it to yield electric motor output. I will be going over each of these subcomponents in further detail, so please feel free to refer back to this flowchart if anything regarding the overall powertrain is unclear. Here is a 3D model of what the overall design will look like. As you can see, there are 12 individual pedaling stations, each with its own generator and chain and sprocket mechanism. Smaller electrical components, such as regulators, diodes, and the bus bar, are not seen in this 3D model, as its purpose is just to show a physical representation of what the design will look like. Zooming in here, you can see what an individual pedaling station will look like in conjunction with its respective generator. Now that you have a good understanding of the overall functionality of our design and its drivetrain, I'll go into more detail on each individual subcomponent and deliverable. As mentioned before, each rider pedals on a chain and sprocket. This chain and sprocket will consist of standard bicycle parts such as pedals, a crankset, bottom bracket assembly, chainring, and a chain. This chain and sprocket system will deliver the human power to the generator. Research revealed that riders will be pedaling at a maximum and minimum speed of 100 RPM and 60 RPM respectively. This is to be considered when selecting the generator's rated operating speed and gearbox ratio. For power output, the average rider will generate about 100 watts, with the upper limit being around 200 to 300 watts. Considering this, the generator should be rated for at least 300 watts. Considering these generator requirements, we selected a MECH 24-volt, 350-watt permanent magnet motor as a generator. The reason we used a permanent magnet motor as a generator is because it generates DC power and does not require an additional power source. This generator is rated for 3000 RPM and 350 watts, and it comes with a built-in gearbox of 10-to-1 and a 9-tooth sprocket. Knowing the ideal input speed to be about 100 RPM, the ideal chainring tooth number is 27. The closest available size for the chainring was 25 teeth. Thus, the rider can provide the generator's rated speed while riding at an ideal cadence of approximately 100 RPM. A boost voltage regulator is used to take the DC power from the generator and transform it into a higher usable voltage. The regulator is also used to take the fluctuating voltage from the generator and regulate it into a constant voltage. The generator will output a maximum of 24 volts. The required voltage is about 55 volts. Therefore, in order to provide an adequate voltage potential, the generator output must be boosted from 24 volts to 55. This led us to select this 1500 watt Drock boost voltage regulator, whose specifications can be seen in the table on the screen. The current limiting diode is used to ensure that the current pulled off the generator never exceeds a set maximum. The reason for this is the generator will be required to generate a specified voltage, which means that only the current will vary. If the current increases too much due to heavy draw from the motor controller, a large torque will be produced, exceeding the rider's ability to pedal. The boost voltage regulator we have chosen already has built-in current limiting diodes. The blocking diode is used to ensure that no power flows back into the generator, turning it into a motor. This is a very important safety consideration for our design. After all of the input power has been collected through the bus bar, a second blocking diode is implemented to ensure the energy from the battery never flows towards the riders, as this would potentially turn the riders' generators into motors if their individual blocking diodes were to fail. The battery will supply a majority of the energy for the electric motors, as the amount of energy required is far more than 12 riders will be able to generate. Based on our energy calculations, 3100 watt-hours with high current discharge is required. After market investigation, the 60 amp hour 48 volt Life MN P04 prismatic battery has been selected as it fits our energy requirements. Details on the specifications for this battery can be seen in the table on the screen. The selected electric motor is a 48 volt 10 kilowatt BLDC motor, as the lower voltage is safer, and this will allow us to have a lower voltage battery, which means the riders will not need high torque while pedaling to produce energy. The vendor Golden Motors offers a 10 kilowatt BLDC with a gearbox and differential. This is the method we have chosen to transfer power to the wheels. The image on the screen shows a drawing of the differential gear bridge. This motor will allow the vehicle to travel up to 40 kilometers per hour, which does satisfy the engineering specifications and user requirements. The chassis will be made using steel hollow structural sections, primarily rectangular 3-inch by 2-inch sections, supplemented with 2x2 and 1x1 inch sections. The resulting structure will be 200 inches in length, 69 inches wide, and 23 inches tall. An FEA analysis reveals that the maximum von Mises stress on the structure will be 27.49 MPa. This means that the structure will be able to withstand the weight of all of the riders and the parts, with a safety factor of 12.7. We built and tested this prototype to demonstrate the design's performance in regards to the chain and sprocket, generator, and boost voltage regulator. Due to COVID-19 restrictions, we had to make do with making the frame out of wood rather than actually machining parts. The main reason we decided to build this prototype is to show the overall functionality of each of these components in conjunction with one another. The other reason is so that tests could be performed to characterize the generator and its torque characteristics. Calculations revealed that 30 ohms is required to represent the load of the bike. Due to COVID-19 limitations, the closest thing to this load available was 4 25-watt 8.2 ohm resistors in series, which provide 32.8 ohms and is rated for 100 watts. Using this load, an initial test was conducted to verify the performance on the generator without the boost voltage regulator. The results were that at 100 pedal RPM, only 14.8 watts are being generated, and the voltage never exceeds 28 volts, even at max RPM. A second test was then conducted with the same load, but with the boost voltage regulator. The result was that 55 volts and 92.2 watts were achieved before the torque was too great to overcome. This means that the system performed as intended because it output 55 volts and around 100 watts. The power curves for each of these two tests can be seen on your screen. Here is a video demonstration of the prototype in action. As you can see, the voltage output is reaching 55 volts due to the performance of the boost voltage regulator. As we pan around, you can see that the chain and sprocket mechanism is working in conjunction with the generator and the boost voltage regulator to generate this output. Including an element of competition was an important design aspect for this project. For this reason, watt meters are to be used for each rider and the whole team to measure their power output. This watt meter is rated for 60 volts and 150 amps. It has many functions, including data logging and power monitoring. Using these functions, the client can decide how to create a unique team building competition. In conclusion, our hybrid electric model for this proposed 10 to 12 person bicycle design project is a successful and innovative solution that meets all of our client needs. However, several future work items still need to be considered. Firstly, the interaction between the generator, battery, and motor is still unknown. Further testing should be conducted in order to fully understand how all of these components will interact with each other. Second, the steering, braking, and wheels need to be designed and specified. The chassis also needs to be optimized for manufacturing. Also, an electrical expert needs to review the powertrain, and the suspension needs to be investigated. It's possible that suspension won't be required for this bike's applications. On behalf of myself, Jesse, Daniel, and Hadi, thank you very much for watching our MECH 400 final capstone presentation. We hope you enjoyed.